and had our simple single capacitor, single resistor circuit, and using Kirchhoff's rules, came up with this, and then recognized that this just isn't an equation. This is not algebra, in the sense that you guys are used to algebra being a collection of constants that are related together. These are functions. They are things that themselves are related to another variable, time. The word you would probably use would be parametric, but that's not really the right word to use here. Parametric functions are relating algebra functions together, but these are related by the differential, which makes them beyond a parametric relationship. So this equation isn't telling you the same thing you might think it is. It's telling you how two other relationships are related together. This is how much charge is building up on the capacitor. The rate at which charge is deposited on the capacitor depends on how fast the charges are moving through the circuit. But how fast the charges are moving through the circuit depends on how much charge is on the capacitor. So these things are interrelated. The longer we allow the circuit to go, the less current there's going to be in the circuit. But how are they related? Which mathematical function is the one that would govern that the current is decreasing as the charge is also increasing? There's a lot of possibilities of functions where when one thing increases, the other one decreases. Calculus is the magic. It's the voodoo that's going to tell us how they're related. But if you've never done this kind of mathematics before, then it is almost magic. So for those of you who have calculus, you know the last step. You know what it's going to take to go from the integral symbol to an answer. But for you guys who've never had calculus before, and those of you who even have, it's going from here to that last step where you're really trying to demonstrate you understand how these relationships and how these variables are actually related. And the first one is recognizing that when you have charge and current in the same relationship, then you have a differential equation. This doesn't happen that often where you can recognize a differential equation. That's going to be harder as the year progresses. And we have other things that are related, and you have to know that when you see these things together, that you have a differential equation, that current is related to the flow of charge. That's the first part of this, is creating the differential equation that will then determine how we will process the rest of this function. Now from here, I told you guys that the process you're going to use is splitting the differential, meaning we have to get this and turn it into something that can be integrated. And I said to you the things that you have to do. You have to isolate the differential first, which means getting it to its side by itself. Maybe getting the R and peeling it away. So you have just the differential here. Then splitting the differential so that you have one differential on one side of the equation and a different differential on the other. And then collecting your variables so that any integratable variable is located on the proper side with this differential. So for us, that means this entire thing having to be moved over with dq. So you get dt equals 1 over all of this garbage. Okay, so this process, splitting a differential, leads to this moment when you can now employ the rules you have been given in calculus to take the integral. This is analogous to finding a function and then plugging in your numbers to get an answer. This is the calculus analog, except that our answer is going to be a function. We're going to get q as a function of t. So this isn't going to produce a numerical result. It's going to produce an algebra equation. An algebra equation that we know when we take its derivative will fit into the original equation we started with. Unfortunately, this is why you take calculus for 3 semesters. So that you can learn every possible method for conducting an integral, even integrals that have no actual answer. You'll learn all the stuff in calculus 2 about dealing with Taylor expansions and other forms of basically the ways machines will take integrals when there is no way to get an actual, algebraic solution. Now, I do this a little different than the way your calculus teacher does. We are going to take the integral both sides. I like making it a definite integral, which means I like aligning your limits of integration. This is what I call applying boundary conditions to your problem, because our problem has boundary conditions, things that we know are true at specific moments of our circuit. For example, we know that at time 0, at the start of this, the charge began with 0 charge. This would be different if we were discharging the capacitor. If we're discharging the capacitor, which we're going to do next, at time 0, the capacitor would have charge, and I'd have to put that starting charge here. So identifying our starting variables is just the beginning. It's giving us our boundaries. The way I've seen Mr. Brashear teach this is to do this as an indefinite integral, leaving it with a constant in the end that you will then plug in your boundary conditions to figure out the constant. I don't like doing it that way, but there's nothing wrong with doing it that way if that's how your training has prepared you for this. Because you have to do something here that many students find uncomfortable, and that is I'm just putting in the future variable that I'm going to use for the top part of my integral. I know at some time t in the future, the capacitor will have some charge q. So these represent the future variable holders, the q as a function of t that I'm going to get in the end. The only things that are actually my boundary condition generally are my starting positions. Now, what happens next is you do calculus. You execute the integral using whatever tools you have to use to execute an integral. Now, the one on the left, we've done. I feel no sympathy for those of you who can't figure out what to do with the one on the left. There's no variable there, or number, so we assume a 1, that this is t to the 0 power. It has to be t because we are dealing with dt right here. So we assume t to the 0 power, and then we treat this like a polynomial antiderivative, meaning I'm going to add 1 to the exponent on t, and then divide by the new exponent, and I get t evaluated from 0 to t. That is the antiderivative, and then I apply my limits, so I get t minus 0. That's the left side. And we've done this before, and those of you in mechanics, we've done it before, but you need to be able to do that. Are there any questions about this? The right side, you've got a problem, don't you? It's not clean. There is no direct step from here to here. So for those of you in calculus, you know what you have to do here. This is a U-sub problem, and U-sub will solve this. And for us, we usually don't need anything more complicated than U-sub. I say usually. There are times where sometimes you have to use something else. If you have to use anything greater than U-sub, it'll be on the integral table that's provided on your equation sheets. If you look on your equation sheets, third page of the equation, is it the second page? It's got to be third page of the equation sheets is an integral table. Is it the third page?
Well, I printed it in the wrong order because I wanted these on the same page.
But one of them has an integral table and then a bunch of geometry information. So you're going to see a whole bunch of integrals and their outcomes. So I don't remember if it's the first page or the last page, though. I think it's the same page that has the geometry stuff on it.
Yeah, it is.
So, unfortunately, you need to learn how to do U-sub, and you need to recognize when to use U-sub. For you guys who have calculus, you understand what I'm saying. So you guys who have not had calculus or are not advanced in calculus yet, U-substitution is a way of creating an integral that matches an archetype you already know. You are going to substitute in another function that will appear on your calculus table, something that you know how to take the integral of. But you don't know what to do here to replace it. You don't have enough experience. So I'm not going to be able to expect very much from you in the beginning. But what this also means is in your notes right now, you should be building that this is something I'm going to have to practice and look for. I can tell you one honest truth here is that we only have 2 or 3 of these. 2 or 3 times you would ever have to use U-sub, and they all will look exactly the same. I would like this to look like 1 over a variable with respect to that variable. That's what I'm trying to create. Because I know the integral of this. So that's a substitution I want to do. So to do that substitution, U-sub is a pretty straightforward process, but it's a process with step 1, creating your substitution. This is the substitution I wish to do. I wish to substitute this function with a U. Thus, it's called U-substitution because the traditional variable we use in substitution is U. So it's not like Y-O-U substitution. It's the letter U substitution. So when they've all been saying U-sub, it's because they use U. You could use anything you want here. So any letter will work. But because it's called U-sub, I will traditionally use U. You're just substituting. But the first thing you have to do is realize that we're substituting in to replace Q. So we not only need to have a substitution, we also have to have the derivative of our substitution. So step 1, come up with your substitution. Step 2, take the derivative with respect to your integrating variable. So I'm going to take du dq. I have to take the derivative of both sides. And I'm being a little long-winded here. I would never do this if I was actually working problem out, being this long-winded. But I'm trying to ensure that all the people who are fresh here see the real steps as much as possible. This is a polynomial. And unless it has anything to do with Q, it's a constant. So when I distribute this differential, taking the derivative of the EMF divided by R, that's 0. It's a constant. It is not changing with respect to Q. The resistor and the potential difference have nothing to do with what Q happens to be at the time. So they're constants. So the first thing will be 0. Now I need to apply ddq to Q over RC. Well, that wouldn't be any difference than saying ddx of 2x, which we've done something similar before. You would just take the 2 out and then take the derivative of x with respect to x, which means this would just be 2. Do the same thing over there. I'm going to take the derivative of, I'm going to take dq of 1 over RC times Q. 1 over RC is just a constant. So when I take this derivative, this is going to be 1 over RC times ddq of Q. And the derivative of Q with respect to Q, polynomial rule. That's Q to the 1. Take 1 away from 1 and you get Q to the 0. This just becomes 1. So what I'm left with is that du dq equals 1 over RC. That's the derivative of U with respect to Q. Yep.
What happened to the EMF? What did you do with that?
It's a constant. Basically, this is times Q to the 0 power. So I bring the 0 out front. It zeroes everything out. There is no change in that variable with respect to Q. So now we have to sub this in for our function and for dq. So the last step is to solve this for dq. So cross multiply is enough, and I get negative RC du equals dq. We are now prepared to take our integral. We have two things that we will use in our substitution to be able to take this integral. Yes, sir?
How come when you took the constant of the EMF over R, it became... Wait, no, I got it. It's
Okay.
dq, so it's
Right. Right. We all okay? Can I keep going? I want to make sure. Look, if you have any question now's the time to ask. Yes, sir.
When you were doing the integral in the first place, why couldn't you take it all, like, if everything else is a constant, why couldn't you just take them out of the integral in the first place? And then just take...
Because there's no way to, I have to do it by factoring. The only thing I could actually factor out is, I guess, the 1 over r. So I could have factored that out. But that doesn't offer me much of an advantage, because I can't factor out the e. It's in the denominator. There's no way to separate that. Remember, this is all multiplied by dq. So there's, unless I can factor it in a traditional sense to get outside the integral, there is no way for me to do that. Yes, sir?
Is it not possible to split the fractions as well?
I could get like denominators, but I will still have q in the denominator of this fraction, regardless of what I do.
Over 1. Could you just flip it and then do it that way?
No. I mean, I'm not exactly sure what you're suggesting, but this is not the same as that.
He means like
No,
R
it's like
over.
R over EMF minus RC over Q.
So that's getting common denominators. You're saying to do...
No, just
No.
get rid of the over 1. I'm saying that bottom is currently to the negative. You're getting rid of the over 1.
So R over.
Stop telling me what to do and walk your ass up here and put it on the board. Because I'm not getting it clearly. And I want to. I want to continue from here, because now you have to use sub, which actually is just doing this substitution. Now, traditionally, I'm supposed to also translate my limits. I believe that starts getting cumbersome, so I'm not going to. So we're just going to focus on the fact that we're dealing with an indefinite integral for a moment. But I've done my u sub now. So I had to substitute in for dq and substitute in for my function. Everybody see the substitutions okay? It's this substitution and this substitution.
Oh.
Go ahead, but you better not make me go too far back.
It's on the white part. I forgot this to get how'd you get...
It's more patience than I showed the person who opened my door second period. Still hearing about that today. All right, so at this point, I'm going to blow through the rest of this. This is a constant. Let's pull it all the way out of my integral. You have a general archetype for this, meaning you have a function that matches taking the integral of 1 over u with respect to u. And you're supposed to know what it is. Now, if you haven't had calculus, you're right. You might not. Except that we've seen this one already once this year. But I want to be very clear. You should know what to do next. The integral of 1 over u with respect to u is just the natural log. So on the left side, I still have t. But on the right side, I'm going to have minus RC natural log of u. Now, There's a lot that has to happen now. So before we jump for joy that we're done, we're not even close. Because A, we haven't put in our limits. But we can't put in our limits until we put back what we did for our substitution. So your next step, and I'm not writing all of this stuff out. I hope you're writing notes to yourself about each step, because I'm not. So if you didn't write any notes to yourself, I'm sorry. But all those words were supposed to be there for you to be able to write things down. But we have to sub back in our original function that has Q in it. And then we have to apply our limits. So if you remember, our original function for U and we have to put in our limits. Okay? It's still all equal to T. I know this is a lot. I'm taking an entire day to do one differential equation. Our next step, though, is just put in our limits. So T equals minus RC natural log of E over R minus Q over RC minus natural log of E over R minus 0 over RC. I know, it's a lot. I don't care. You are smart people. Use paper. Don't try and cram it all into a single line. And recognize we were just following a set of steps. I had to plug in my limits, though. But I will say that my limits have a 0 in them. So this will be a little bit simpler than it looks, but not much. Just means that one term is zeroed out. Now, I've been putting in the absolute value bars because that's what Mr. Brashear really likes. He likes those absolute value bars. And I probably need to keep them because I guess it is possible that this could be negative. And we know we can't take the natural log of a negative number. That's what the absolute value bars are in there to remind us about when it comes to math. But we do have rules for natural logs. And if we want to simplify this, we probably should follow our rules for natural logs. Because although we could stop right now and say we're done, we want Q as a function of T. And right now we have T as a function of Q. So we need to solve this for Q. Now I should just stop and say do it because you guys have all finished pre-algebra and can do this. But my experience has been that a gentler hand might be nicer. But you guys who have the experience should be ahead of me right now. And you should be racing to try and beat me to the end. Because you know things, you're smart. Me, I'm going to be deliberate. T equals negative RC. When you subtract two logarithms, it's the same as dividing them. Everybody okay? Well, I have a natural log, and inside the natural log is Q. So I need to get rid of the natural log. So my next step is going to be to get the natural log by itself so I can raise both sides to the base of E. That's how you get rid of a natural log. So my next step is going to be to divide both sides by that negative RC. And I am aware that what's inside the parentheses can be simplified. I just know that there's really no reason to do it yet. But every step of the algebra I'm doing here is algebra you've done. At least that's what it says in your transcript. But now I'm going to raise everything to a base of e. So on the left side, I get e to the minus t over rc. And on the right side, I just get e over r minus q over rc divided by e over r. Raising the natural log to a base of e effectively cancels out the natural log. Now I can solve for q. It ain't pretty, but I can do it. I can multiply both sides by e over r. So just multiply both sides by this. I want q by itself. So I'll add it to both sides. And I'm going to subtract this term from both sides. There's an r in every term. You guys see that okay, right? Do you see that? So can I just get rid of the r that's in every term without causing too much of a ruckus? And would it bother you too much if I collected the e? Because I think that's an okay thing to do. So I'm going to collect the e. So I get q over c equals e to the 1 minus e minus t over rc. Almost done. Multiply both sides by c. And technically, that's it. Now, that was a whole hell of a lot. I mean, a lot. Remember where we started. One little tiny circuit with one capacitor, one resistor, and one power supply. Let me show you some things. If this resistor wasn't here, and I just connected the power supply directly to the capacitor, what would be the charge on the capacitor after it come to full charge? Yes, sir. That's right. Charge on the capacitor would be EC. So, and when it is fully charged, that would be the charge in the capacitor. That's what has to be out front, because everything in here is a unitless quantity. So there's no units inside there. I have to have something that's in terms of coulombs in charge. So EC is the potential max charge on the capacitor. Look at what's happening inside those parentheses. When t equals 0, what is e to the 0 power? So at time 0, everything in here is 0. Right? It's 1 minus 1. So at time 0, the charge in the capacitor is 0. Exactly as we thought. Now, as t increases, what happens to this term? gets smaller, right? It's e to the negative t. So as t gets bigger, this becomes 1 over an ever increasing number, which means when t's been going for a long time, this term disappears, which means after a long time, my capacitor will eventually have maximum charge. Now, what determines how long is a long time? That does. RC is our time constant. It might not be obvious to you, but RC has to be in seconds. It has to be, meaning ohm farad has to work out to units of seconds. It has to, because I can't raise e to the power of a number that isn't unitless. So this has to be seconds divided by seconds. You should try it, because you've seen what ohm and farad are when it comes to their units. They're a mess. They're a nightmare. And it almost cancel out to leave me with seconds. I'll leave that to you, because I think I've done enough algebra for the day. On the other hand, if you were to plot this, and I need you to just give me a second. This is an asymptotic function. It looks like this. Tomorrow, I have an RC circuit. We're setting it up. We're going to take a look at what this looks like over time. And then you guys are going to do the lab where you'll prove that the time constant is equal to RC. We've got nice big 1 farad capacitors, which allows the system to take several seconds to come up to full charge. It's easy. It's a great lab, and it produces perfect data. But yeah, that was a lot today. I know it was a lot. So I appreciate you guys hanging in there till the end. And, oof.
How would you put